Hello everyone, welcome back to my Calculus 1 series. In today's lesson we'll be going over function transformations and combinations. So to start off, let's pretend that we have this arbitrary function called f of x. So let's assume that this is it right here, and this is the base function that we're going to be dealing with in all examples. So let's also pretend that we have this constant called c, and let's assume that for the purposes of this video that c will always be greater than 0. So this will be the constraint on c, and wherever we see this constant, let's assume that it is always greater than 0. So now for the first transformation, if we grab a look here, it is y equals f of x plus c. So let's take a look at the original function y equals f of x. If we look at it, let's look at a point like here, for example, where x equals 0. If x equals 0, let's give this, let's say, a value. Let's say that this is 2, like the y value is 2. So if we're going to add a positive constant, this c value, to the value of 2, it will always rise up. This point will be moved up to somewhere, let's say here, let's say c isn't too large for this case. So the point that was initially at 2, let's say it's going to move up. Now we can do the same for almost any point on the graph here. Let's choose, for example, this point right here. At let's say this is -2, and let's say that this is a value of 2.5. If we are going to add a positive c value to here, we know that this point as well will move up. And just for the purposes of this example, let's take another point per se here, right? This point would most likely be 2, and then maybe the value of it is, let's say, 4. So if we add a positive constant to 4, this point will also move up to somewhere here. And now if we look at it, this is starting to resemble the original function that we had. However, it seems that it has been moved up by this constant factor of c. So the new graph of f of x plus c will just be a copy of the original graph f of x, but moved up by some constant factor. So what we can conclude by adding this constant factor to the initial function f of x is that it will move the graph c units upward. So we can call this a vertical translation c units upward. Now moving on to the next example, we could see that the new function here, y equals f of x minus c, is likely to be very similar to the one that we had before. We can actually apply the same method to figure out what is going to happen to it, but it may be pretty obvious that if c is a positive number and we are subtracting this positive number from the original value of y, then it's likely that the graph were to move downward. But I can show you this anyways. Let's take the same point as where we started from in the other example here. And let's say the value here was 2. If we were to take away any positive constant factor, the graph will definitely move downward, meaning this point also will move downward by a factor of c. Let's say maybe c in this case is, let's say c equals to -3. So we will get to -1. And we can do this for almost any point. This point will likely be down here. This point might be up here. And so we will get the same looking graph, however, just moved downward c units. So we can conclude that y equals f of x minus c is a vertical translation c units downward. So now let's take a look at this function, y equals f of x minus c. What we can see immediately is that c is now within these parentheses, and c is getting taken away directly from the value of x. So to take a look at how this affects the function, let's take a look at this point right here, where x equals 0. Initially, at x equals 0, we have f of 0. But with this new constant factor of c, let's assume for this case that c is equal to 1, we will now be getting f of 0 minus 1, which is now f of minus 1. So the value previously of where x was -1 will now be put to the place where 0 is. So this value right here will be put where 0 is. Let's look at another point like right here. Let's say that here x equals 1. So previously we had f of 1 there, But now with this new transformation, and we would have f of 1 minus 1 because we chose c to equal 1. So now the new value there would be f of 0. And f of 0 would lie somewhere here. So let's take a look at this final value right here. And let's say that this right here was minus 2. So previously, before the transformation, we had f of minus 2 there. However, with the transformation, we had f of minus 2 minus c, which is 1. So now we would be getting f of minus 3, which is this value right here. So the previous f of minus 3 would now be where f of minus 2 is. So we can clearly see now that connecting these points, we have a similar function. However, it is moved over rightward by c units. So we can conclude that y equals f of x minus c is a horizontal shift c units rightward. Now looking at this function, we can see that we have the opposite of what we had before. We now have a plus c. So let's have a similar approach and figure out what the new graph will look like. If we take this point right here, let's assume that the x value of it is minus 1. We can see that previously, before, we had f of minus 1 there. However, with this new c constant, let's call it in this case again a 1, we now have f of minus 1 plus 1, which is f of 0. So whatever was at f of 0, which is right here, will now be put in the place of f of minus 1. So it will be here. Now let's take a look at another point, maybe something here. So this is the x-coordinate of 1. Previously, before the transformation, we had f of 1 there. But with this transformation, we'd have f of 1 plus the c, which is 1. So we would have f of 2. Whatever was previously in f of 2, which is likely to be here, is now put in the place of f of 1. So this f of 2 coordinate right here moves over to the spot of f of 1. If we were to connect these points, we would see that we would get a graph something like this. Essentially, what we can conclude is that adding a constant factor to the x-coordinate of a function will move the function over c units leftward. So to conclude, y equals f of x plus c is a horizontal shift c units leftward. Moving on to the next set of transformations, we will now be transforming the graph by multiplying it by a constant factor of c. However, for the purposes of this example, let's assume that c is greater than 1. We can apply a similar approach to figure out what the new transformed graph will look like in a similar manner to what we did in the previous examples. Let's take this value right here, where the x-coordinate is 0, and the y-coordinate is likely to be 1. If we were to multiply this y-coordinate by a constant factor greater than 1, we would be getting a value larger than 1. So the new point is likely to be somewhere up here. If we do this for another set of points, we will see what happens to the function. Let's take this point as another example. Let's say that the value here at f of 1 is likely to be 2. If we were to multiply this value by a constant factor greater than 1, the new point would likely be somewhere here. For the final point, let's take something over here. Now here, the x value is likely to be minus 2. If we were to take 0.5 and multiply by a constant factor of something greater than 1, we would likely get a point somewhere up here. Connecting these dots, we can see that the new function is very similar to the old function. However, it is stretched by a factor of c. We can conclude that multiplying our function by a constant factor of c, which is greater than 1, will vertically stretch our function by a factor of c. Moving on to the next example, this right here is very similar to the one that we had before, except now we are multiplying our function by something that is less than 1. Since c always has to remain greater than 1, we know that its reciprocal will always be less than 1. We can apply a similar approach as to what we did in the previous example. Let's take this point right here. The value of x equals 0 from the previous example was 1. If we were to multiply this value by any value less than 1, we would likely get a number less than the value itself. So the new point would likely be somewhere here. Taking a similar point from the other example, let's take something here. This right here is likely to be f of 1, and we said that the y value is going to equal 2. If we were to multiply 2 by any value less than 1, we know that the number it would yield is less than the number itself, in this case 2. So the value would end up somewhere here. And to stay consistent, let's take a similar point that we did from the previous example, which was here. We said that it would be f of minus 2, and the value of it would be 0.5. If we were to multiply 0.5 by another number, which is less than 1, we know that we would get an even smaller number. So the value of the new point would be somewhere here. If we connect these dots, we can now see that we get a new function. However, it is compressed by a factor of 1 over c. So we can conclude that multiplying our function by a factor of 1 over c will vertically shrink our graph by a factor of 1 over c. Moving on to the next example, we can see that c has now been brought inside the brackets and it is directly multiplying the value of x. Let's use the same approach as the one we were using before. Let's take this point right here and say that this is f of 1 and it equals to a value of 2. If we were to multiply this x value by any factor greater than 1, we know that we would get a value that is greater than 1. So for the purposes of this, let's say that c equals 2. So now the new value that we would be getting is f of 2 times 1, which is f of 2. So all of a sudden, the value that we previously had at f of 2 is now in the spot of f of 1. The value of f of 2 is likely to be here, so we will now draw this value in the spot of f of 1. Let's take another point somewhere here. The value here was previously f of minus 1, and multiplying this inner value by a constant factor of c, which is greater than 1, will yield us a value that is even more negative. In this case, since c is minus 2, we can say that f of 2 times minus 1 is equal to f of minus 2. So whatever value we had here is now going to take the place of the value that we had before. Now, if we were to connect these points, we could see that we would get a function something like this. And as we see, the interval from which the function spans on has shrunk. So we can conclude that multiplying the x-coordinate by a factor of c will horizontally shrink our function. Now for this example, we will take this value right here and say that it was f of 1. If we were to take this x-coordinate of 1 and multiply it by a value smaller than 1, we would get another value which is less than the value that it initially had. So for this example, let's say c is equal to 2. So we previously had f of 1, and now multiplying it by a half will yield us f of 1/2. So if we look, f of 1/2 is somewhere here, and now this new value will be in the spot of where f of 1 used to be. If we now look at a value, let's say here, and say that this was f of 1 previously, multiplying it by 1 over 2 will now give us a new value of negative 1/2. So f of negative 1/2 is likely to be somewhere here, and this new value will now take the spot of where f of 1 previously used to be. If we were to connect these dots, we would get a function something like this. You can notice now that the interval of the function is much larger than what it used to be before. Essentially, what we can conclude is that multiplying the x-coordinate by a factor of 1 over c will stretch the graph by a factor of c. On to the last set of transformations, we look at negating the y value first. Let's apply a similar approach and take an arbitrary point on this graph. Let's say that this was previously f of 1 and the value of it was 1. If we were to now apply the transformation and multiply this previous y value by a negative, our new f of 1 would equal minus 1. So the point would now lie somewhere here. If we were to take, let's say, this value right here and say that this was f of 0 and initially it was 0.5, Applying our transformation to it now would yield that f of 0 is negative 0.5, which would lie somewhere here. Lastly, let's take another point somewhere here. Let's say that this was f of minus 1 and it was 0.45. Applying our transformation, our new point at f of minus 1 would equal to minus 0.45, and it would lie somewhere here. Connecting these dots, we see that we have a function that will go something like this. We can see that this is the exact same function, however reflected about this x-axis. We can conclude by saying that multiplying your function by a negative value will reflect it about the x-axis. For the very last example, we are now negating the x value. Let's apply a similar approach as we did to the last problem. Let's take this point right here and say that this was f of 1 and it equaled 1. But now, using this new transform function, we would get that f of minus 1 should now be in place of where f of 1 originally used to be. So f of minus 1, let's say, is somewhere around here. We would now take the value of f of minus 1 and plot it into the spot of where f of 1 used to be, which is here. So now let's deal with f of minus 1. Initially, it was f of minus 1. But applying the new rule where the x-coordinate gets negated, we should, in place of f of minus 1, get f of 1. So you could see that these two coordinates basically exchanged places. Essentially, if we go on and continue this with a series of points, we will see that the function would look something like this. And we can conclude that it is the same function, however reflected about this y-axis. So we can conclude that multiplying the x-coordinate by a negative value will reflect our function about the y-axis. Now on to function combinations. For these function combinations, we will be referring to f of x as x squared plus x and g of x as the square root of x plus 3. Essentially, these are just made up functions that I've created to show examples on how we can create function combinations. So the first function combination is the addition of two functions. Here is the notation for it. You can sometimes see it written as f of x plus g of x, or you can see it written as f plus g of x. And now, using the example that we have before, essentially this will be x squared plus x plus the square root of x plus 3. Now, the second combination of functions we can see is the subtraction of functions. And the notation for that would be f of x minus g of x, or you can sometimes see f minus g of x. And using the two examples, we can see that it would be x squared plus x minus the square root of x plus 3. The third combination of functions would be a multiplication of functions. And the notation for that would be f of x times g of x, or you may sometimes see fg of x. And now, using our example, it would be x squared plus x times square root of x plus 3, which is equal to x squared times the square root of x plus 3 plus x times the square root of x plus 3. The fourth combination of functions we could see is the division of functions, and the notation for that would be f of x divided by g of x, which would be equal to saying f over g of x, provided that g of x not equal to 0. Using our example, we would see that this would be x squared plus x divided by the square root of x plus 3. Now, I'm not going to simplify that, but you could rationalize it. The last combination of functions that we could see is something called a composition of functions. And the notation for that would be f of g of x, or we could say that it would be f, and then we would use this circle of g of x. And using our example, this would mean that we would take whatever g of x was and plug it into the x values of f. So if we were to look at what f was x squared plus x. Into every single x value, we would plug in the value of g of x, which was the square root of x plus 3. So the value of f of g of x would be the square root of x plus 3 squared plus the square root of x plus 3. And we can go on to simplify this right here, but I'm not going to for the purpose of this video. Now, an important thing to know that f of g of x is not equal to g of f of x. I will show you what g of f of x looks like. Essentially what we're going to do is we're going to take g of x, which is x plus 3, and into every x value we are going to plug in the value of f of x, which is x squared plus x. So the value of that would be the square root of x, and for x we plug in f of x, so it would be x squared plus x and then plus 3. That is the value of g of f of x. So as you can tell, f of g of x are not equal to each other. So that concludes my tutorial on function transformations and combinations. If this tutorial has helped you out, please leave a like and feel free to join the Discord group where I will help people with their math problems. Also, if you are new to this channel, please leave a like, comment, and subscribe. It would be greatly appreciated, and I will see everyone in the next video.